So thank you for those very gracious words to me and Sasu for inviting me here. It's a very special honor to be here at Helsinki, University of Helsinki, because this was the birthplace of Linux. And the entire computer science community is grateful to all of you here at Helsinki for what you helped to nurture and create, and we are benefiting from that. So my talk today really is all about both the cloud and the edge. And so without further ado, let's get started. So the first and most important thing to note is that cloud computing is big. If you ask Google how big it is, the answer you get back is shown on this slide. It's basically it was on the order of $500 billion in 2023, with projections to go over $2 trillion in 10 years. So these numbers are difficult to comprehend. How big is $500 billion? The same year that this measurement was reported, the total GDP of the United States was $28 trillion. China was about half of that, and Japan was a bit smaller. So the way to think about this is close to 2% of the GDP of the United States comes from cloud computing. 2%. That is a mind-boggling number. Now, if you ask a different source, you get slightly different answers. You should take all these statistics with a large grain of salt, because I have no clue how they come up with such accurate numbers, okay? But on the order of $500 to $600 billion in 2023 is widely acknowledged to be the total footprint of cloud computing. But it's not only money that cloud computing has delivered. The Nobel Prize in Physics, all of you know, went to Geoff Hinton for his creation of deep neural networks and machine learning as such a pioneering approach to solving problems even in the natural sciences. So that was in physics, and that was last year, 2024. What not so many people know is that the Nobel Prize in Chemistry was also awarded to researchers who worked on aspects of machine learning, applying them to protein structure. So the citation from the Nobel Committee that is shown here explains that the software that was created called AlphaFold 2 by these researchers, Dennis Hassabis and John Jumper, is basically able to predict the three-dimensional folding of virtually every protein known. This was considered an impossible feat only a decade ago. So this is also due to cloud computing. So we have here something that is 2% of the GDP of the United States, helps people win the Nobel Prize in Physics, or people win the Nobel Prize in Chemistry. What is the secret? What is behind the power of the cloud? Like so much else that is very powerful, at the heart of cloud computing is only one simple idea. Just one, but it's very powerful. And that idea is consolidation. The notion that if you can concentrate an enormous amount of computing resources rather than dispersing them, that concentration will deliver to you huge benefits, resulting in all the benefits that I've just shown you in the previous slides. In particular, it delivers huge benefits in the form of a new business model for computing, which turns out to be very influential. It has important security implications, and it offers you superb connectivity, which is not attainable anywhere else. So If you look at a typical data center, this is what it might look like. Row upon row upon row of machines. The one thing you do not see here are people. And that's really an important part of the story. It is the case that hiring talented IT staff and then having a data center, even a small one, making sure that air conditioning and all the other things are provided is a big expense, and it's a capital expense. You have to put the money up front, you have to pay the people even at vacations and so on. This whole thing is a very expensive proposition. And further, if you're a startup company, capital expenditure is not treated very well. You have to depreciate it over a number of years. And so the ability to hand all of this over to somebody else, Amazon or Microsoft or somebody, and then just pay them a monthly fee based on how much computing you use, that model turns out to be hugely beneficial for many, many people, large enterprises, startups, etc. And the thing about this business model is it's hundreds of years old. It has been used in real estate. People buy property, they pay the maintenance and take care of it. You just pay them rent. This has been going on very successfully, and that's the model. In the area of security, a data center has extremely strong perimeter security, which means getting through the outer barrier is very difficult. It's like a fortress. Breaking through is hard. Further, because the administration of the data center has been carefully optimized, you need very, very few people. And it's well known in security that the biggest vulnerability comes from people. And by minimizing the attack surface on people, you also ensure security. So security is improved in cloud computing. Last of all, because you have a very carefully conditioned environment inside a data center, you are able to provide superb network connectivity. 10 gigabits per second is considered very low today. 40 gigabits per second is common. There are experimental local area networks which are terabit per second networks. So the value of this is it allows you to use hundreds of machines, thousands of machines in parallel computations. So paradigms such as MapReduce are well known to all of you. We teach it to undergraduates. But many of the applications, such as AlphaFold 2 and others, would not be possible if we did not have this capability. So how big is a data center? On average, a data center today is about 100,000 square meters, which is about 1 million square feet. And the biggest one is about 1 order of magnitude bigger in Mongolia and China. For those of you who think in terms of playing fields, this is about the size of 17 football fields, American football fields, not soccer fields, right? So that's 17 football fields in size is huge. There are a few tens of these data centers in each region for each of the big players, Amazon, Google, and Microsoft. And within each region, there are typically 3 to 5 individual data centers. So the idea is that they are typically backups of each other, they support each other, it's possible to load share across them. So on the order of a few hundred data centers cover the entire globe. So this is the picture. And what results from it looks like this. You have a few hundred data centers from each of the major tech companies distributed across the globe. and they have superb connectivity, fiber optic connectivity between them. So their latency is almost speed of light, maybe a factor of 5 or 2 to 5 above speed of light, and the bandwidth is excellent. So I've spent 5 minutes now singing the praises of cloud computing. As you all know, in the real world, nothing comes for free. So what are we paying? Something's not quite right. We are sacrificing something, and what is that? The answer is, all of this has been achieved by making connectivity one-dimensional. Wired connectivity is inherently one-dimensional. The problem is that the Earth's surface is three-dimensional. So if you wish to connect your home, your smartphone, your laptop, etc., then the picture has to look something like what's up here. You have this inner core of data centers which have superb connectivity, and then all of the computing we actually do is in the periphery. And the connectivity between the periphery and the core is necessarily multi-hop, because it is too expensive to direct connect everything on Earth. So when I came from Pittsburgh to Helsinki, I had to fly through Chicago, which is a big hub, then through Frankfurt, and then get here. And each of those hubs is a potential problem area. In other words, it is possible for me to have delays, to have cancellations, etc., at each one of these points. And the same thing happens in the real world with multi-hop networking. So the price of consolidation is that the average data center is many hops away from the average end user. And when lightly loaded, without too much queuing delay, this is usually not a big problem. So the best case is fine. The average case might be okay, but the worst case is horrible. And for many, many applications, the user experience is determined not by the average case, but by the worst case. So here are some measurements that we took 1 year ago. We have here a smartphone. This is in my office. We have a server in my lab, just 1 floor below and a few hundred feet away. And we also have over here, we also have over here the data center of Amazon in Virginia, Amazon East. So speed of light distance between the smartphone and the Amazon data center is about 6 milliseconds. Okay? Speed of light distance. So for connectivity, if you do trace route between the smartphone and the Amazon data center, the packet first needs to go to a cell tower on 5G, and then through the internal network to the internet, and then from the internet to Amazon. And the total number of hops is 12 hops. So if you decide this is too many hops, and you say, okay, instead of using Amazon, let me use the CMU server. The distance between the smartphone and the CMU server is just a few hundred feet, 100 meters at the most. It should be very few hops. Sorry, that's not how it works. It's more hops, 15 hops. The reason is because T-Mobile does not connect to the internet anywhere near Pittsburgh. All the packets from Pittsburgh have to travel across the state of Pennsylvania, get to the city called Philadelphia, which is at the eastern end, The peering point for T-Mobile is located there, and then comes back on the internet back to Pittsburgh. And so you actually take more hops. If you use a private 4G wireless CBRS wireless network, which we have installed, this should be the path from the smartphone to our antenna to the internet to AWS, and that turns out to be 11 hops. So no matter what you do, going through the internet, going through the telecom infrastructure, to get to any of these data centers, even your own private data center, is non-trivial, many hops. And so the best approach turns out to be to directly connect your private network to the server, and this gives you 4 hops. Now these are mean values. We also have a distribution because, as I mentioned to you, it is the worst case, the tail of the distribution that matters, not just the mean. And you can see on this graph that the local cases are very sharp, but the ones that go over the internet have very diffuse curves, indicating that the jitter and the tail are very long. So the question all of you are thinking is, does latency really matter? Today, all those $500 billion worth of GDP has been achieved with this infrastructure. So what's the problem? The answer is, today's applications, web-based applications, have been co-evolved with the internet infrastructure. And as a result, they are latency tolerant. If you design an application that tries to be much more deeply immersive, much less latency tolerant, then the limitations of this infrastructure become immediately apparent. So let me give you an example. This is an augmented reality application. So I use my smartphone and I hold it up outside my window, and the video stream is transmitted to somewhere or processed locally, and the buildings are identified, and the labels are sent back so that on my screen it says, if I'm in Manhattan, it says this is the Empire State Building, this is the Chrysler Tower, etc. It's a trivial, you might assign this as an undergraduate project in your class to do this kind of project today. If you were to do all of the processing on the smartphone, this is what the curve would look like. So this is how many milliseconds it takes for one of those responses. So this is a cumulative distribution function. And you can see here that because the processing, the computer vision is done on the smartphone, it's not very fast, so it's not a great curve. If, on the other hand, I ship the image, the video frames, to Amazon East, which is close to CMU, this is the curve that you get. If I ship it to Amazon West, which is the other end of the country, you can see the additional transcontinental latency being added to it. And if I do the back end in Asia, where the server is located in Singapore, oh, sorry, that is Dublin, Ireland, which is EU, and then that is Asia. Now you notice that in each of these curves there's a fuzzy band around the core. That is the variability in the results, the variance of the results. So as you go further away, you also see greater variability in the tail of the latency. So if I used a cloudlet located 1 hop away, this is the curve that I get. Okay? The tail is short and the mean is extremely low. And this is the kind of curve that you need for the class of applications I'm going to describe to you in the rest of this talk. So we have done these measurements for many, many other applications. We don't have time in this talk to go through all of them. They're in the papers that are in the various forums. Here is one more example. This is visualization. And you have to interpret this a little differently. This is the number of frames per second, instantaneous frame rate. Higher is better. So being on the right side is good, being on the left side is bad. So if I perform the visualization locally on a desktop, I get this nice curve with very high frame rate, close to 60 frames a second mean. If I execute it over a network with 33 milliseconds, that's all, delay, the frame rate drops dramatically down to barely 15 frames a second. And beyond that, additional latency makes it even worse. So these are the kinds of applications where the latency of the internet seriously matters and is going to prevent us from creating the class of applications that we wish to create. So the solution is to bring the cloud closer, is to create a tier of computing that we call a cloudlet. So if you think of the cloud as tier 1, and you think of the devices like your smartphone, your laptop, your wearable device as tier 3, these are swap devices, size, weight, and power optimized devices. Then the cloudlet occupies tier 2. It's one wireless hop away, so less than 20 milliseconds ideally, latency, with a very short tail. And very important to appreciate that the compute in here is identical to the compute in the cloud. This means when some code is released in the cloud, the effort involved in making it execute in the cloudlet is zero. There's no software porting, there's no need to reduce the precision, etc. It's the same hardware, it's just a smaller data center located close by. That's why it's called a cloudlet. It is like a cloud, just nearby. Okay? So, I've shown this cloudlet as a black box. In practice, it could take many form factors. You could imagine a cloudlet in your vehicle, a cloudlet on a ship, on an aircraft, etc. Or in a building, you could have a small rack in a closet somewhere that serves as the cloudlet. So edge computing is a non-trivial market today. In 2023, it was a $16 billion market. And according to some other estimates, it is expected to grow very substantially by 2030. Now, how anybody is able to make predictions to 2 decimal places is mind-boggling. So don't trust any of those second digits, okay? The important point to note is that edge computing is real, it is already delivering revenue, and it's going to grow substantially. Most importantly, the proof is asking, what is driving this growth? I've already given you one reason, which is if you have applications that require low latency, you have no choice. You have to have edge computing. But it's not the only reason. Even a much simpler use case, if I have a large number of video cameras, each 4K video camera at 30 frames a second consumes on average 30 megabits per second. If I have 10 video cameras covering a certain area, that's 300 megabits per second total data rate. Very soon, just the bandwidth demand of processing all the video in the cloud becomes too expensive. It's uneconomical. It's much easier to put a cloudlet close by, push the processing close, and then ship back the much reduced output of the video analytics to the cloud. So that is another important use case that is driving edge computing. Privacy turns out to be a big, big driver. For good reason, people are suspicious of putting all the data in the cloud. If you have a video camera in your house, and your children play in your backyard, you may not be quite so happy with the security company getting all of your private data. Filtering out, for example, faces, or blacking them out, and so on, is effectively denaturing the data before it is transmitted to the cloud. And this turns out to be an important use case for edge computing. There are many, many applications in which the backhaul to the internet can fail. Military applications, disaster recovery, deployments in developing countries, many, many IoT deployments, all from urban areas, have this property. And there, the ability to use a cloudlet, the same way you buy battery backup for your desktop, to offer you transient disconnected operation, is a very powerful use case. And last but not least, it turns out that there are non-technical reasons to push processing to the edge. Finland is part of the EU, and the EU has the GDP privacy law, which says that certain kinds of data cannot be exported from the national boundary. So the only way to access it is to push the processing to where the data is, rather than sending it to the data center. So data provenance may not be a huge volume of data, but it's crucial. So for all these reasons, edge computing is going to grow over the next decade and beyond. Under different names, companies, all of the major tech companies, have embraced the cloudlet concept. So Google calls it Google Distributed Cloud. This is a proprietary name for the concept. And if you read their webpage, I have a screenshot of it on this slide, it says here, with Google Distributed Cloud, you can extend the latest in AI models and AI-optimized infrastructure without compromising on data residency, latency, or connectivity. Okay? Amazon calls their cloudlets Amazon Outposts. And the blurb there, describing what Outposts can do for you, says it supports workloads and devices requiring low latency access, etc. And Microsoft calls their product Azure Local. It doesn't matter what they call it, they're all cloudlets. Okay? So, in the last part of my talk, I want to ask the question, assuming a few years from now cloudlets become widespread, edge computing becomes just as important as cloud computing is today. How will that transform society? What are the kinds of applications that can emerge, that can make a big difference to us, right? So, about 10 years ago, 2013, 14, my colleagues and I came up with this concept of wearable cognitive assistance. The inspiration was something that every one of us uses every day today, which is GPS navigation. Some of us in this room are old enough to have lived before GPS navigation was possible. There were these old-fashioned things called paper paper maps. Question 1, where am I on this map? Question 2, which way should I hold it? Question 3, where should I go on this map? Etc., etc., etc. Today, it's trivial. Whether you're driving or you're walking, the app tells you, take the next right, and then take the exit that comes shortly thereafter. And if you fail to take the exit, fail to follow the instructions, it catches it and corrects you immediately. Right? So this is very powerful. So the idea is, could you use edge computing and rich sensing, like video cameras, to do this for things other than navigation? When I go to IKEA and I buy this kit, they give you this sheet of paper to tell you how to put it together. I don't know about all of you, but I'm never very successful in correctly using that sheet of paper. It would be so much better if an app on my smartphone could say, next, take the long screw and insert it into this hole. And if I pick the wrong screw, it says, no, not that one, the other one. Right? So we actually demonstrated the feasibility of this. And today, 10 years later, you notice here, these are companies in healthcare and other areas which are applying this concept, taking it from the lab to more commercial, real-world practice. It's going to take some time, but the idea is too powerful to ignore, because it's one of the ways in which human productivity can be dramatically improved. And in fact, industry is starting to embrace wearable cognitive assistance. So here is a company, Pluto Men. It's not my company, I've had nothing to do with it, which talks about how basically wearable cognitive assistance, they use a brand name for their version of this concept, but that's okay. And it's not just this startup company. Siemens is using it, Lockheed Martin is using it, and in general, the use of this technology, this approach, in any kind of high-value, small-volume manufacturing, aerospace, etc., is becoming much more prevalent. So, the one thing that none of them do is prevent you from making errors. Okay? Mishaps cost pain and they cost money. In the United States, approximately 3 million emergency department visits annually for older adults. 1 in 4 adults will experience a fall each year. 1 in 4. And as we get older, we become part of that statistic. So, if you look outside aging, and you look at manufacturing, human error is a big source of waste, scrap, quality control, etc. Somewhere between 5 to 30% of the cost of manufacturing comes from mistakes. So, could wearable technology, low latency wearable technology, help us to solve this problem? So the inspiration is something that has been around with us for about 10 years, called driver assist. My car, I drive an old car, it's a Subaru Forester. When I bought it, it was brand new, it had a new technology in it called EyeSight. It's a stereoscopic camera system. It looks at the road ahead, and if I get too close to the car in front, it alerts me. And in fact, it even can brake my car to prevent it from colliding. If I wander from the lane, it beeps at me. if my driving pattern indicates that perhaps I might be getting drowsy, it speaks to me and tells me, wake up. And you can also set it on adaptive cruise control so that if the car in front of you brakes, your car automatically slows down. You know, this was new 10 years ago, but every company now, Mercedes, BMW, Volvo, you name it, they all have their own proprietary versions of these subjects. And it's very successful. It's estimated that a huge number of crashes, injuries, and dollars are saved by this technology. You can see the statistics on this slide. So it's serious. This is high value, makes a big difference. But notice that although my car is safer, old people still fall. Okay? Why can't we do mishap prevention outside the car? The answer is that an automobile can easily carry the sensors, the compute, including the high-end GPU, and the energy needed for the computation easily. At highway speeds, it carries passengers, luggage, carrying an extra compute and some sensors. There's no big deal. But on a person, people don't wish to carry a lot of weight. Nobody wants a backpack to help me prevent myself from falling. So, none other than our General Chair Sumi showed us 25 years ago that you could make the room smart. So his pioneering work on a system called Gator Tech House, is that correct? Did I use the correct name? Gator Tech House was one of the pioneering experiments that showed you could build a specialized building with sensors embedded in it so that it was able to be a safe environment for people who might have loss of sensory ability. The problem with it is it required you to build a special house. And if you leave the house, the protection vanishes. What we want is wearable technology that goes with the user. Imagine I do nothing more than wear a special pair of glasses. You're already wearing, many people in this room are wearing glasses. If my glasses could alert me before I stumble, or help the worker just before he or she makes the mistake, if the person is fatigued, drowsy, distracted, we all do stupid things and we regret it after doing them. But the time to help is just so full. And so the idea is, imagine a platform that allows you to do this, and you have apps which are specialized to different settings and different use cases that help you to prevent mishaps. So the goal here is to prevent adverse events before their occurrence. And very important to appreciate that this is the exact opposite of what OpenAI and Google's Gemini are trying to do. All of these large language models are trying to do full AI. The goal here is much more specialized. Like the driver assist system, or like the GPS navigation, the goal is to create narrowly focused applications which are able to deliver value in specific settings, but to do it fast enough that in fact it works. So none of these has been implemented yet. We are working on this in our lab. We're partway through. Ask us in a year, and hopefully we'll be able to show you a demo. But this is where we are. So alerting factory settings and workers, alert medical personnel if they're about to make the mistake, use the wrong tool or do something wrong, you like to alert them. The important thing is, just like the driver assist, the system remains quiet and does not in any way slow the user while they're working. And so you can go through many other examples of this kind. The system architecture that we are using for this is called wingman, because wingman is a term for a buddy who keeps you out of trouble. Okay? And so you have a wearable device, in this case a smart glass, wireless connectivity, typically 5G, Wi-Fi, or someday 6G, to a cloudlet. Running on the cloudlet are specialized cognitive modules which do the computer vision and other sensory analysis and interpret it to warn of the possible mishap ahead. Now notice that we do have the cloud here, but the cloud is not in the critical path of alerts. It's too far away. The cloud does have a job to do. The job of the cloud is to tune the code in the cloudlet continuously to improve it using the specific context of the user at the moment. So retune the models, perhaps do fine-tuning of the machine learning that is inside those cognitive engines, and to do it based on the current actions and context of the user. But that is not latency critical, so doing it in the cloud works well. So we come now to the latter part of the talk, and the question that many of you may be wondering is, in 2025, do I really need to offload computation to the edge? Because your smartphone today is a lot more powerful than the smartphone was 5 years ago. Google has created tensor processing units for all of the Pixel phones. Apple has neural processing engines on the iPhones. And these things can do serious machine learning. Large language models have specialized versions that run on smartphones. My colleague Tianqi Chen is one of the people who does this kind of work. So the question is, to do real-time AI with the speed and the accuracy for mishap prevention, do you still need edge computing? Would I do it all on device? Now we need a definition of real-time AI. So I have chosen 100 milliseconds as a threshold. You have to be able to take sensor input after the sensing has been done, do the processing, and be prepared to trigger an alert. That's the total budget that you have, 100 milliseconds. Does not include the actual sensing time or the actual actuation time. So, as I mentioned to you a second ago, these specialized processors can be enormously effective. This table here shows that if the metric of interest is gigaflops per joule, right? Energy efficient computing, which is what you need on a wearable device. There's no question that becoming more specialized and less general is huge. So you see up there that it's a factor of 50. Now those results are fairly old, about 15 years old, but the underlying principle has not changed. That as you specialized and move away from CPU to its GPU to its various XPUs down to ASICs. ASICs are purely combinatorial. Even the machine learning model is burned into the ASIC. If you do that, you can get 2 orders of magnitude speed up, which is huge. So with all this, do we still need edge offload? So I'm going to show you results. We obtained these results 2 weeks ago. So I haven't had the time to take those results and make them look nice. So this is cut and paste from our paper. But hopefully you can see it. It's clearly now. So the task in question is object detection. That's a well understood task. And the metric is mean average precision. So anyone working in computer vision is a pretty standard metric for object detection. And here are all the machine learning models that we looked at on the left side. They vary enormously in accuracy. So these have very few parameters, 3.9 million to 8.1 million. The ones at the bottom are huge, 64 million is the largest one. And you can see that the accuracy is directly correlated to the size of the model. Some of these models come in 8-bit integer variants. You lose some, the lower precision costs you something in accuracy. So you can see here that these, which can run on a smartphone, give you something below 30% accuracy. The YOLO models come in both full precision and limited precision variants. You can see that there's a cost to lowering the precision. And these, at the bottom, are too big to run on any smartphone today. So basically the message is in 2025, if you need accuracy of above 50%, roughly, you need to do edge offload. There's no other way to do it. And we haven't even talked about speed yet. That is the subject of the even more dense slide, which is the next one. Here are 3 devices, state-of-the-art devices. So Google Pixel 9, that's these 2 columns. The middle is O, which is OnePlus, which is the fastest smartphone you can purchase commercially today. And then R is the Ranio wearable device, which is a state-of-the-art Android wearable device, smart glasses. The things in red mean it is too slow. It's above 100 milliseconds, which means you could not do it there. The takeaway message here is as the accuracy increases, you notice even the smallest of the YOLOs takes 60 milliseconds. And anything more accurate than that is too slow to run, even on a Pixel 9. The really high accuracy models down here simply cannot be run at all on the smartphones. But if you use edge offload to a cloudlet, even the largest of these is doable in much less than 100 milliseconds. So at least in 2025, it is very clear that you still need edge offload. And oh, by the way, these numbers include the network overhead. This column shows the same thing without the network overhead. So the network overhead is significant, but this is the portion that edge computing helps with. If you try to do this in the cloud, it would be much worse. So we have exhaustively studied other computer vision applications, instance segmentation, activity recognition, object tracking, classification. The message is the same. Today, if you need only modest accuracy, you can do it on device. You don't need cloud computing, you don't need edge computing. But if you need accuracies which are closer to state-of-the-art, and you need them at speeds below 100 milliseconds, you have no choice, and it doesn't. Remember that every year, very smart people come up with even bigger and better AI models, and they are more compute intensive than the ones that exist today. So edge computing has challenges of its own. I mentioned to you that security was one of the areas where cloud computing benefited from the consolidation. The dispersion of edge computing means that you have to revisit security. All of the old ideas on detecting, tampering, tamper resistance, all of these ideas become relevant again. Consolidation lowered system administration costs. Dispersion means technologies of which services, this is IEEE Services Conference, so very relevant. Administration of distributed infrastructure becomes very relevant. Scaling. When I have a flash cloud, the ability to suddenly bring as much compute to bear as I need becomes a challenge. And last but not least, figuring out how to charge. What is a successful business model? It's still not been figured out for cloud, for edge computing. Cloud computing was easy. The rental model property for real estate works. How do you charge for something you don't even see? Because edge computing is transparent. So this is a question that needs to be answered. So, as my very last slide, I'd like you to reflect on the last 50 or so minutes where I've been speaking. The information flow has mostly come through words, but it's also come through my gestures, the body language. You have been processing all of these sensor streams in real time, doing natural language, computer vision, activity recognition in parallel. You have not been using edge offload, and I haven't either. And human beings, by definition, are the standards by which AI is judged. So how do we do it? The answer is that nature has had 1 billion years to co-evolve the applications like natural language and the AI hardware, the specialized neural circuitry in our brains, to do all this accurately and in real time. No, we're not that patient. We don't want to wait another 1 billion years. We want to build superhuman systems in 10 years. 8 orders of magnitude shorter, faster evolution. Edge computing, where you're able to purely use software to improve your system and defer the translation into ASICs until the application has solidified and stabilized, is the only way to achieve it. And so for the foreseeable future, both edge and cloud computing have important roles to play that are distinct, but they're both going to be supremely influential in our future. Thank you.